What is up, guys? Today we're going to be talking about the scientific method. And the scientific method is basically a systematic, can't spell sometimes, approach used in scientific study across all branches of science. So these branches of science can include biology, chemistry, physics, and even other branches or denominations. And so the scientific method is something that is very useful and that we are able to use across all branches of science. And so let's jump right in. So the scientific method begins with observations. And what these observations are is existing knowledge. So these are things you already know going into your experiments. And your observations, this is the existing knowledge. How you get it, it's the acts of gathering information. So I'm going to abbreviate information info. And so these observations can be separated into two categories. You've got quantitative and qualitative. So qualitative data is, and I know I'm starting on the right, is information that describes a characteristic. I'm going to abbreviate without W/out. So characteristic without numerical values. So this could be something like saying it's red or it's blue, hard, soft, brittle, something like that. Quantitative data is numerical information. So qualitative data uses no numbers. Quantitative data is numbers. So this could be stuff like 10 grams. It is 4.5 units. Or something's moving at a speed of 5.6 meters per second. Notice these all have numbers in them, and the focus is on your numbers. And so from these observations, so we're going to start this down here. So we have observations. Again, from observations, it moves into making a hypothesis. And so hypothesis is a tentative explanation for what has been observed. This, we're just going to shorten it down to a testable statement. Hypothesis is something you say that you can test. And so from the hypothesis, we move into the first loop of the scientific method, which is experimenting. So somebody's going to conduct experiments, and an experiment is a set of controlled observations. And so observations and experiments are not that different. It's just observations are the information that forms the reason. Experiments are the information that tests the reason to prove or disprove it. Not really information, it's more methods to gather information. So the experiments are the methods to get information to prove or disprove the hypothesis. The observations are the information that make the hypothesis. So since experiments are controlled, the experimenter is usually trying to figure out if one variable is causing something to happen. He or she wants to generally form a good hypothesis that can test just one condition. And so the condition that the experimenter tests, I'm going to write it right down here, is called the dependent variable. And I'm going to put that in a different color so this way it's not confused. We'll choose red. So it's called the dependent variable. And so the experimenter will also change one factor. This factor is called the independent variable. I kind of wrote that terribly, but so the dependent variable is what changes in response. The independent variable is what the experimenter changes. And so the way I remember that is I'm the experimenter. I change the independent to see how the dependent changes in response. So that can be a handy little trick to help you all out, is I change the independent. Anyways, once the experimenter completes his or her experiments, he or she's going to reach the next stage of the loop, which is the conclusion. So conclusions are basically judgments. And these judgments are based off of data. So the data you collect in the experiment is the basis for the conclusion. So this data and the experiment kind of link back up with each other. So, and a conclusion is either going to support or it's going to reject a hypothesis. There is no in between. It either says, yes, it's good, or no, it's not good. And so, from the conclusion, we may reach, if it does not support the hypothesis, we're going to reach the next stage, which is revise the hypothesis. And so this stage, if the hypothesis was not supported by the conclusion, then they revise it. Scientists revise the hypothesis if it was proven false. So if it was proven false, then they'll revise it and they'll run more experiments. But if the conclusion supported the hypothesis, the experimenter is going to set everything up again and run the experiment many, many more times. And he or she is even going to record every step of the process, so this way other scientists can replicate the experiments and perform even more experiments to either support or not support this original hypothesis. So if the hypothesis is supported, we can move on into the second loop. So we'll put an X to say it doesn't support and a check to say it does support. So if it doesn't support, it keeps in the loop. If it supports, then it can eventually move on to becoming a theory. And a theory is an explanation of a natural phenomenon based on many observations and investigations over time. So a theory basically is just an explanation of a thing that happens. So this can be as simple as it's an explanation of why, if I were to drop my pen that I'm writing with, why it falls instead of just floating there. That can be a theory. And it was a theory until Isaac Newton pretty much proved it to be more than just a theory. But we'll get into that later. So, from a theory, we move into Ooh, the next stage, because like hypothesis, a theory is subject to experiments because scientists want to test it even more. And they love checking and rechecking as to whether something is correct. If the theory is supported, it remains a theory. If not, so we're going to put our X, then scientist goes into revising the theory to make a new theory, a better theory, or something like that. So when they revise a theory, suddenly they're set up with a new theory. So, and this will start the loop over with a new theory, experimenting about it, and deciding whether it's supported. So from there, it branches off into two sections: theory and law. The theory is as discussed earlier. It's an explanation of a natural phenomenon based on many experiments or many observations and investigations over time. A scientific law is different. It is a relationship in nature supported by many experiments. So I'm just going to say a relationship in nature because that's basically what it is. Scientific laws are generally unable to be disproven, so those are accepted by everyone. There's no way anybody can prove it wrong. However, people could form theories about how these scientific laws operate if they choose, and the cycle might start back over with observations, hypothesis, experimenting, making a theory, and then maybe even making a law about a law. So, one good example of a scientific theory would be Einstein's theory of relativity, which everybody knows as E equals mc squared. E is energy, m is mass, and c is the speed of light. This is something that's an explanation for a natural phenomenon, which is attempting to explain how much energy an object would have traveling at the speed of light squared, an object of mass, that is. However, it can't be disproven or anything like that, mainly because we don't possess the means to launch an object at the speed of light squared. Now, one example of a scientific law would be Newton's law of universal gravitation, which basically boils down to all particles have some kind of attraction to each other, that is also dependent upon their mass and the distance they are from each other. So closer objects with greater mass will have greater attraction to each other, whereas further objects with less mass will have less attraction to each other. In fact, you have gravitational attraction to things if you're bigger than them. However, Earth's gravitational pull is many, many times greater than your own, so nothing pulls towards you because your attraction is very small compared to Earth's. And so this has been the scientific method, and I hope this is helpful.